Maybe we can get started for today. Just a keynote from ODE class, because we are using this repeatedly, but I still see that sometimes we get confused. So a second derivative, uh, second order ODE, linear ODE, you have just two terms, a very simple boundary value problem. So it has solution in two forms: cos and sine if lambda is positive, and cos hyperbolic and sine hyperbolic if lambda is negative. And we are not generally we are not dealing with lambda negative when we are solving linear PDEs. Is lambda negative means kind of solution blows up. So we are not much worried about the second solution. Okay. So today we are going to do some working. So we are given a function. We want to find a wave equation. I think I add a word as so. You may have a PDE which has multiple elementary solution. So here a function is given, and you want to find a wave equation that has it as a solution. And this is a technique we normally call a method of manufactured solution or manufactured PDE. So if I have a PDE, if I have a solution, I can manufacture a PDE as I want. So if we want a wave equation, then you take this function, differentiate twice in t and differentiate twice in x, and then plug into the wave equation. Maybe you will have a non-homogeneous term or you will have a homogeneous term. If it is not a solution of a non-homogeneous wave equation, definitely you will get an additional term and you will put that term. So that you can construct a wave equation, that you know the solution. But now if I reverse So this is like a game. So you try a solution, it does not work, try anything, it does not work, try anything. If you are lucky, you can find one. So sometimes it would be very easy depending on the equation. Sometimes it is not easy. So this is a non-homogeneous wave equation. So for non-homogeneous wave equation, a simplest approach would be if we try to get an elementary solution by error and trial. So then we can give it a try. So here I will give you, or maybe I can rewrite or verify So I have given you a function. You can verify that this is a solution. So maybe the purpose of this example to tell you that there are PDEs that is not easy to see a particular solution. This is one. You can give it a try 2, 3 times, 4 times, 5 times, 7 times, 8 times. Maybe you cannot get it, and sometimes you can get it. But then I have given you the solution, so you can take that and verify that. Yeah. So, but now we have a question in our mind that is there any way we can actually use a method and then we can construct a solution. So that is something we'll be learning as we go. So I'm going one step at a time. So now I am trying to raise some questions that you can see that, well, this is something doable, but I don't know how to do. So there might be a method, and we look for the method. So let's now look for some strategy method for solving non-homogeneous wave equation in finite domain. Well, I will say homogeneous or non-homogeneous. So I will first start with homogeneous, because when it comes to finite domain wave equation, the characteristic we discussed that it goes from minus infinity to infinity. When it comes to finite domain, it first needs to understand how we can use separation variable at this stage, because we cannot use D'Alembert's method. So let's first go with an example that we already discussed, so we can work it out here to get further practice. And you can immediately notice that because of the domain, we can apply D'Alembert's method, but that might be too tedious because we have to extend the solution beyond 0 to 1 up to minus infinity and up to plus infinity, and that reflection method is possible but could be complicated. So let's do this with separation of variable. And if we have a maybe before we discuss this, we can also remind ourselves for dealing with non-homogeneous terms. So if we want to deal with non-homogeneous wave equation, somehow, as I just posted an example, somehow you find an elementary solution by trial and error. Or if you know later on, if you know a Fourier series method or another method that can be applied. But for now, let's say if we try to develop technique, find an elementary solution, say this is Wxt. So this satisfies the non-homogeneous equation. Then define u xt to be wxt plus bxt, and this will lead to a homogeneous equation for bxt. Okay, so that means the technical work is on solving the homogeneous part. Non-homogeneous part so far error and trial, and if we fail to error and trial, we have to look for something else. So let's put a period here and say, okay, let's assume that for the homogeneous part we can find a solution by error and trial like this one. Okay. So separation of variable, as perhaps we mentioned earlier, for wave equation we will use S of x times h of t, because wave equation we cannot simplify like heat equation. So we substitute the solution as if a product of special function and a time dependent function, and then substitute back to the wave equation. So you get on the left hand side S h double prime t, and on the right hand side S double prime x h of t, and then we separate h double prime t divided by h of t, S double prime x divided by S of x, and we'll use equal to lambda, and we'll take lambda positive. Okay, so then we have two boundary value problem. One is S double prime x plus lambda s equals 0, S prime 0 equals 0, S prime 1 equals 0. So you look at those two boundary conditions. So the first boundary condition is a derivative with respect to x, so that applies to S prime. Second boundary condition is derivative with respect to x, so that also applies to S prime. Okay. Then you get another one, which is H double prime plus lambda H t equals 0. And we don't have boundary condition, but we could come back later on and manipulate those two initial conditions for each part. So perhaps we leave for now this way and solve for eigenfunctions. So by looking at this eigenvalue problem is second order ODE, lambda positive. So the solutions are sines and cosines. So we can work out a constant times sine plus a constant times cos, and by looking at the boundary condition we can figure out, well, the derivative boundary condition. So derivative of sine will not vanish at x equal to 0 and x equal to 1. Derivative of cos will vanish at x equal to 0 and x equals 1. My eigenfunctions will be and which is due to boundary condition. And then we can construct a solution. So the solution now, because in heat equation I had e to the power minus lambda t for time dependent part. So this time I have not solved for time dependent part, but maybe I can write it down from n from 0 to infinity, and maybe I will also get an eigenfunction for this second order ODE in time, which is h n t, and then I will get cos n pi x. So one way to think about the limit, because this is cos, and without depending on Fourier series, this is cos. So if I have eigenfunction cos, I still can go from n from 0 up to infinity, but at n equals 0, the eigenfunction sine n pi x will be 0. So there is no need to start from 0. We start counting from 0, obviously, for all cases. For cos, starting from n equals 0, we will get a special eigenfunction cos 0, which is 1, which is a constant. So we can start from n equals 0. Okay, so now if we try to solve for the time dependent part, so time dependent part would be h of n t a n cos. So the solution is square root of lambda, and lambda is already found. Maybe I can just write down in one step. And h of n t n pi t So from here, the special part, we figured out what is lambda. So then you look for a special eigenfunction. Which is n equals 0. Lambda is n square pi square is 0. Any confusion about why lambda is n square pi square? Then is a good question. Without doing calculation, if you look at this part of this boundary value problem, so the solution will be cos square root of lambda x, lambda cos square root of lambda x, and then you have to satisfy the boundary condition. Okay. Yeah. Square root of lambda will be n pi, right? Yeah. Square root of lambda will be n pi. Yeah. Okay. So for this special case, what we have here, since lambda is 0, h 0 double prime t plus 0 times h of t equals 0. So you get h prime t is a constant a, and then h0t is at plus b, or c1t plus c2, does not matter the symbol. So special case, I have that. I can also have a special case for the special case for special eigen function, but since it is cos n pi x, when I put n equals 0, I get it 1. So I don't need to work it out. If I work it out, I will get ax plus b, and then I will evaluate a and b. So that is possible, or I can figure it out from here. So in that case, I can write down the solution. Okay, is that complete? What is missing? So I have to look at, I'm looking at this part here. So h of n t is this part. So then cos of n pi x. So I'm coming from here to here. Cos of n pi x. Okay, so maybe I put in equation number 1 here. That will be useful to refer to where I'm going from one step to the next step. Right? So now we can use orthogonality. So how do we use orthogonality? To use orthogonality, we look for the initial condition and apply it to the initial condition. So I have two initial conditions. Let's first look for the first initial condition, which is ux0. And ux0 is given 2 sine square 2 pi x. 2 sine square 2 pi x equals, if you evaluate in equation 1, then the first term, s0, sn is cos n pi x. So s0 is cos 0 pi x, which is 1. And h of t, h0t is, let me just highlight it. So this is h0t. And then I evaluate that it at t equals 0, so that becomes b. plus. Okay, so if you set t equals 0, this term is 1 and this term is 0. So this entire sum will be just half of that. So an cos n pi x. So the time dependent part will be gone. And I like this approach. It's very nice mathematics here that I can calculate very easily without difficulty, right? So now maybe we can just go backward to high school and see what is 2 sine square 2 pi x. So that is a trig identity, right? 2 sine square theta is 1 minus cos 2 theta. 2 sine square theta is 1 minus cos 2 theta. So I can use that 1 minus cos 4 pi x. Yep, up. That is a mistake. 1 to infinity an cos n pi x. So just recall the orthogonality. 0 to L cos m pi x divided by L. You multiply cos n pi x divided by L. Hopefully readable. Equals, maybe I can just use the space below, equals 0, m is not equal to n. And if it is not, if m is equal to n, then half of the interval. If m is not equal to n, then it is 0. If m is equal to n, that is half of the interval, L over 2. And remember, m equals n equals 0 is a special case. Okay, so if I multiply by cos 0 n t, if I multiply this equation by cos 0 n t and integrate it, then because of the orthogonality, this term is 0, because this m is 4 and n is 0, this term will be 0. So I will immediately get 1 equals b. Orthogonality, let me just zero n pi x. That is a 0. Okay. And then multiply by cos n pi, and for n equals 1, n equals 2, n equals 3, if I look at in the left hand side, only n equals 4 will survive. It's 4 pi x. So on the left hand side, we will have for n equals 4, negative 0 to, what is my interval, 0 to 1, cos 4 pi x, cos 4 pi x dx equals, on the right hand side will be f4 cos 4 pi x cos 4 pi x, right? And good thing that you are worried about the orthogonality formula value. value is not needed in this case because this integral just cancels out. Because this is a number, it just cancels out. So you get minus 1 equals a4 and an equals 0 for n is not equal to 4, 0. Okay. So we have something, maybe we can write that down here. Uxt from equation 1. So from equation 1, I still have on the screen, it is here. So I have b equals 1. So I can write b equals 1 plus at plus b plus sum over you can see that an cos n pi. So I can split this sum. You can look at this part and this part separately. If you do that, perhaps we can write maybe individually. So since I have a minus sign, minus a b4, sorry, f4 sine, sorry, that term is the first term. This one is cos 4 pi t, and then I multiply by cos 4 pi x, 4 pi x, right? And then I can write the other part, n from 1 to infinity bn sine n pi t cos n pi x. So all I have done is I have found the coefficient an. A4 is minus 1, A0 is 1, and every other values are 0. Okay. So now you evaluate that function at t equals 0 after taking the derivative with respect to time. And that is given 0. So you write down 0 equals a evaluate with respect to time. So cos will be sine. When you evaluate at t equals 0, this term will vanish. Plus next term will be n from 1 to infinity bn. Differentiate with respect to t, sine n pi t, you get a coefficient n pi, cos n pi t, sine n pi t, you differentiate with respect to t, you get cos n pi t with a coefficient n pi. Evaluate at t equal to 0, cos n pi 0 is 1, so that is gone. So you have cos n pi x. Okay. And now the orthogonality is straightforward. So multiply by 1 or look at the constant term. You just simply look at the constant term. So a equals 0. This is another way. This time it is very simple. So even you can solve it without knowing orthogonality. Then you compare like term from left hand side and right hand side, and you see that Bn is 0 for all n, because in the left hand side there is no cosine term. So then maybe this is equation 2. So equation 2 implies now uxt equals that's okay, a equals 0. So 1 minus cos 4 pi t cos 4 pi x. So that's done. I just remind you here, use separation of method, separation of variable to solve wave equation on an interval. So if your domain is the interval, then you don't use D'Alembert's method. It is more complicated. Use separation of variable, and very much for the homogeneous part is whatever I have just shown. If it is non-homogeneous, as I started, you find kind of at this point you can think of, well, I can find by error and trial a solution that satisfies my homogeneous. I can manufacture something and then I can go with that. Is there any question for wave equation for this example? Okay. So we look for an example here. Boundary condition will be 0 for, and that is 1 at t is also 0, t is greater than or equal to 0, ut at x 0. Maybe you can first write u at x 0, which is cos squared pi x, and that is sin squared pi x cos pi x. And this one should be straightforward, so I put it as a homework or test case, and maybe you can go ahead to verify if you can derive the solution. You should be able to by using the same approach. Four pi t cos 2 pi x minus over 24 pi sine of 6 pi t cos 3 pi x. This is a very good example to practice. separation of variable method for homogeneous wave equation. And is a nice one. You can follow whatever in the previous example and you can get it. These techniques are described by different instructors in a different way. If you look to textbook, you will see that slightly different way. So it is not relevant like the steps. Which steps comes after what? If you are following my lecture note, you pick it, that's fine. If you look at the textbook and if you follow the style of the textbook, that's also fine. You can look at another textbook. The point here, keep in mind that we are not using Fourier series. We are not assuming that I have a solution in the form of a series and memorizing the series. So the idea is to do math without memorization or as less possible memorization. Okay. So even we're talking about the orthogonality, but we don't need to know exact orthogonality value for those sines and cosines. As you can see that the integrals cancels out and we can just equate the coefficients from left hand side to right hand side without knowing orthogonality. Okay. So in the next exercise, we consider the telegraph equation, which is UTT plus UT minus C square UXX equals 0. U0T equals UX. Sorry, that should be UAT maybe. I can just define the domain here. Okay, at BT equals also 0 equals 0. And I have an initial condition UX 0 f of x and u of t x0 is g of x. Everything looks same except it is a different equation. Use the energy method. To prove that the problem has a unique solution.